Welcome to this session on drilling mechanics and shock and vibrations. This is submodule 2 of 4, where we will focus on vibration mechanisms in drilling. We'll explore axial, torsional and transverse dynamics, along with their mitigation. Let's begin with the learning objectives. In this submodule, we'll start by examining the three principal vibration mechanisms: axial, torsional and transverse. Understanding these is essential for identifying the root causes of drilling dysfunctions. We will then explore stick-slip effects, a common torsional vibration challenge, and review both downhole and surface technologies used to mitigate them. Next, we will evaluate BHA whirl, a particularly damaging form of vibration that can compromise drill string integrity and accelerate wear. From there, we'll discuss practical mitigation tools such as shock subs and advanced shock absorption systems, highlighting where and when they are most effective. Finally, we will look at how to interpret vibration modes overall and connect these insights directly to drilling performance. By the end of this session, you should have a structured understanding of the types of vibrations, their consequences, and the solutions available to reduce their impact. Let's begin with axial vibrations, commonly known as bit bounce. These occur when the bit experiences rapid up and down oscillations while drilling. This is common with insert bits. One key indicator of axial vibration is trilobbing, which occurs at 3 times the rotation per minute of the drill string. This vibration pattern often arises from interaction between the bit and formation, leading to fluctuating axial loading. It's important to note that in most cases the bit does not physically leave the bottom of the hole. Instead, we see variations in weight on bit that create the bounce effect. On the right-hand side, the image challenges us with a question: is the PDC bit leaving the bottom? The point here is to recognize that bounce is not the same as bit liftoff. Instead, it's about stress cycles that fatigue components and reduce efficiency. Understanding axial vibrations is critical because they reduce rate of penetration, damage cutters, and shorten tool life. With this foundation established, let's move next to how we mitigate axial vibrations using shock subs. Shock subs are one of the primary mitigation tools for axial vibrations. Their biggest advantage is their ability to absorb axial shocks effectively. They are relatively inexpensive compared with other solutions and are readily available in most markets, making them an accessible option for many drilling campaigns. To achieve maximum effectiveness, a shock sub must be positioned as close to the bit as possible. This ensures it absorbs the energy where it is generated. However, placing it near the bit can push critical LWD tools further back in the assembly, potentially limiting measurement quality. The mandrel design of a shock sub introduces flexibility into the bottom hole assembly. While this helps absorb shocks, it can sometimes create undesirable directional responses, particularly in deviated wells. Another practical consideration is tool diameter. A rule of thumb suggests the outside diameter should fall between the bit and collar sizes. This often introduces another large OD component into the BHA, which may complicate hole cleaning and directional control. A key point to remember is that a shock sub dampens axial vibration, but shocks tend to have multiple modes. These are not dampened, and in some cases the shock sub can be a weak point in the string, leading to twist off. An optional suggestion is to run a steerable motor, which also provides a dampening effect through its bearing housing. In summary, shock subs remain an excellent first-line defense against axial vibration, but they must be placed and sized carefully to balance benefits and limitations. With axial mitigation covered, let's now move on to torsional vibrations, specifically stick-slip behavior. Stick-slip is one of the most common torsional vibration problems we face. It happens when the bottom hole assembly alternates between sticking and then releasing, creating repeated cycles of stall and sudden acceleration. At the surface, this may appear as fluctuations in torque or RPM, even when the rig is applying steady rotation. One of the most serious aspects of stick-slip is that the bit, or even the entire BHA, may stop rotating altogether. In severe cases, it can even reverse direction briefly, This has significant consequences for cutter life, drive shaft fatigue, and the accuracy of directional drilling. Common indicators include BHA stalling, cycles repeating, surface RPM variation, and torque fluctuations. These symptoms are often visible on surface data, but the root cause lies downhole. Managing stick slip requires a combination of bit design, downhole vibration tools, and sometimes surface control adjustments. Next, we'll focus specifically on bit technology and how certain bit types can help reduce torsional vibration.
First bit that successfully combines PDC and roller cone bit technology for smoother drilling, remarkable torque management, and precise steerability, handling the most complex well profiles and helping operators improve performance and profitability. With the cutting superiority and continuous scraping of diamond bits and the rock-crushing strength of roller cones, Chimera bits have the proven ability to survive highly interbedded formations with smooth drilling and excellent tool face control. When faced with hard and interbedded formation, historically operators have had to choose between running a tungsten carbide insert bit or a PDC bit. The PDC bit makes quick work of the softer formation, but can face cutter damage in transitioning to the harder rock. The TCI bit, however, could drill the hard and soft layered formation reliably, but slowly, and even face maxing out its hours used downhole before reaching the target depth. The Chimera hybrid bit's dual action cutting structures enable it to drill the soft formations faster than a roller cone, while improving the efficiency of drilling through the hard rock compared to PDC bits. Chimera hybrid bits improve tool face control for higher buildup rates, making it a reliable solution for shorter, faster, and higher quality curve intervals.
One way to address torsional vibrations is through bit selection. Certain bit technologies are designed to reduce stick slip by providing smoother engagement with the formation. Starting with the benefits, these bits reduce bit-generated stick slip by distributing forces more evenly. They are especially effective in interbedded formations where hard and soft rock alternate, a condition that often challenges traditional PDC bits. Compared with insert bits, they usually achieve a better rate of penetration. They also improve tool face orientation control when used with motors, which is a significant advantage in directional drilling. However, there are trade-offs. The first is run time. Even with improvements, bearing life still limits roller cone bits compared with PDC alternatives. In carbonates or chert, cutters remain vulnerable to severe wear or cone locking, which can force a premature trip. Additionally, stick slip in directional wells is often BHA induced rather than bit related, meaning bit technology alone cannot always resolve the problem. Steering performance can also be compromised in push-the-bit rotary steerable systems, and optimal ROP may not match that of a pure PDC design. The key takeaway is that while bit technology offers some relief, it is not a universal solution. We must combine it with other downhole and surface strategies. With that in mind, let's now look at downhole technology for stick slip mitigation. Another technology used to reduce stick and slip is the Tomax AST. Let's watch a short video on its operation.
The bottom hole assembly is exposed to large torque variations and vibrations as the bit progresses through constantly changing rock types. Consequently, the bit will stick and slip, resulting in shock loads on vital downhole components. Modern drill bits are optimized to cut the rock driven by weight and rotation, controlled from the surface of the well. However, in changing formations, this remote application of forces can easily contribute to sticking or stalling. The buildup of torque following a stall will eventually cause the formation to break, and the bit will spin out violently. These instabilities are known to be the source for severe vibrations, equipment failures, and slow and costly drilling operations. Tomax has developed its new anti-stall technology to dynamically control and optimize the depth of cut downhole to prevent stalls and vibrations. As the cutters start to dig too deep, the increased torque is dynamically transformed into a decrease in weight on bit. As a result, the cutting depth is reduced, and the bit keeps rotating. These dynamic adjustments are made continuously, accommodating changing conditions and resulting in faster yet safer drilling. This revolutionary technology is the basis for the Tomax anti-stall tool, AST. The AST converts excessive torque into reduced weight on bit by utilising a helical spline. As the torque increases, the helical activation angle increases, shortening the tool. This temporary change in length reduces the effective weight on bit, enabling a decrease in the cutting depth. As the torque reduces, the tool extends, returning weight to the bit. The activation and return parameters of the helix are controlled by a stack of high-strength cone springs. The AST tool is typically placed within 200 feet or 60 meters from the bit and does not require any signal or manipulation from surface in order to function. The Tomax anti-stall tool brings you great benefits in many downhole applications. Drilling difficult formations with strong contrasts and stringers. Drilling with simultaneous hole enlargement. Well intervention using downhole motors and coiled tubing. The use of the AST also opens for a wider choice of drill bits for maximising performance. The anti-stall tool from Tomax. New technology for a new era.
Now watch a video on the SoftTorque system, which is a top drive control device.
Worldwide, thousands of drilling platforms operate constantly in the struggle for reaching oil and gas. One of the challenges drillers face is a common problem called stick slip, whereby the drill head jams and springs free again with force. After this initial burst, the drill bit slows down and gets stuck again. This cycle of sticking and slipping creates many complications like lower rate of penetration, more wear and tear on the drill bit and the downhole equipment, and damage on the well bore. The ElectroProject SoftTorque control system prevents the drill bit from getting into this stick-slip cycle and saves days of operation per well. The system consists of two hardware components, the controller, which is mounted nearby the motor power controls, and the tactile screen, mounted comfortably near the driller. It is easy to install and easy to maintain. The SoftTorque controller regulates the speed of the motor and reacts on the torque fluctuation caused by the sticking drill bit. This process prevents the drill bit from sticking again, resulting in a constant drill speed, improved performance of rotary steerable systems, less wear and tear on downhole tools, reduced bit damage, and increased bit runtime. This all leads to an improved rate of penetration of up to 30% and cost savings of up to millions. Other SoftTorque systems use theoretical models to tune the drill pipe, but ElectroProjects measures reality. Our auto-tune software makes driller interference no longer necessary. Moreover, with the latest ElectroProject advanced SoftTorque system, thin pipe operations, the depth of the drilling and horizontal drilling have improved significantly. Our innovative technique increases drilling performance and saves costs in dozens of drilling platforms all over the world. ElectroProject SoftTorque, preventing stick slip, saving money.
Now let's turn to BHA whirl, which is one of the most destructive vibration mechanisms encountered in drilling. Whirl occurs when the bottom hole assembly rotates eccentrically inside the well bore instead of smoothly on center. This results in the BHA striking the borehole wall repeatedly as it spins. Two types exist, forward whirl and backward whirl. Forward whirl progresses in the same direction as pipe rotation, while backward whirl progresses in the opposite direction. Both induce significant shock loads, but backward whirl is typically more severe because of the high lateral forces applied to tools. Whirl accelerates wear on stabilizers, drill collars, and MWD/LWD housings. It can even damage drill pipe thousands of feet away from the bit due to vibration transmission. Because of this, understanding and identifying whirl early is critical. In the next slide, we'll look at an extreme example of forward whirl. The pictures give a clear visual example of extreme forward whirl in practice. Forward whirl occurs when the BHA rotates in the same direction as the drill string but off-center, causing it to orbit inside the borehole. The image on this slide shows the results: heavy tool body wear, localized damage, and evidence of repeated high-energy impacts. In this case, the tool experienced a continuous forward whirl condition. The rotating assembly repeatedly struck the borehole wall, creating flat spots and deep scarring. Such damage not only weakens the tool structurally, but also reduces measurement reliability for any logging while drilling equipment housed in the same collars. The wear patterns are unmistakable. Smooth areas where the body has polished against the formation, alternating with gouges where impact forces were highest. From an operational perspective, this example underlines the need for proactive mitigation. Once whirl begins, it is very difficult to stop without pulling out of hole. The best defense is optimized stabilization, correct placement of vibration damping tools, and careful control of RPM and weight on bit. This slide reminds us that vibrations do not remain localized at the bit or BHA. They can travel significant distances up the drill string and cause damage far from the source. Here we see an example of a drill pipe that developed a flat spot and one-sided wear pattern. The caption notes that this section of pipe was located more than 2,000 feet away from the bit. The wear was caused by forward whirl transmitting energy upward along the string. Transverse vibrations occur when the bit or BHA oscillates laterally rather than axially or torsionally. A common type is bit whirl, shown here. Bit whirl is most often associated with PDC bits, particularly those with aggressive side cutters. Because their cutting action is non-symmetric, the bit is displaced off-center as it rotates. This causes it to follow an eccentric path within the borehole. On the right side of the slide, we see a diagram showing the path of the bit center. Notice how the bit does not rotate neatly on axis, but instead traces a circular or lobed path. Interestingly, the bit typically follows a trajectory with one more lobe than it has blades, producing an overgauge hole. The key problem is that this eccentric motion creates large lateral shocks, reduces drilling efficiency, and accelerates wear on both the bit and BHA components. In addition, because the hole is enlarged unevenly, directional control becomes more difficult. Bit whirl should be recognized early by monitoring downhole vibration data and interpreting borehole condition indicators. With bit whirl explained, the next slide moves us to BHA whirl, which is the broader assembly level manifestation of this vibration mode. BHA whirl is an escalation of transverse vibration where the entire assembly, not just the bit, moves laterally within the borehole. This slide highlights several key features of BHA whirl. First, the shocks are both large and frequent. As the pipe rotates, the BHA impacts the borehole wall and is then flung across to the opposite side. This process repeats rapidly, generating extremely high energy impacts. Interestingly, the whirl progression is typically anti-clockwise, even though the rotary system itself turns clockwise. This counter-motion arises from the dynamic interaction between pipe rotation and borehole friction. The amount of energy imparted depends directly on wall friction, meaning rougher, higher friction walls create more violent whirl events. The result is greatly increased bending stresses throughout the drill string, particularly at connection points. This leads to accelerated fatigue, housing deformation, and, in extreme cases, catastrophic failure. With transverse vibrations explained, we can now move to the concept of mode coupling, where vibration modes interact with one another. Now let's look at the concept of mode coupling. Mode coupling occurs when different vibration types, axial, torsional, and transverse, interact and reinforce one another. Instead of occurring in isolation, these vibrations can become synchronized, amplifying the overall energy transmitted through the drill string. For example, axial bounce may trigger torsional stick slip by changing the torque applied at the bit. At the same time, lateral whirl may increase bending stresses that align with axial oscillations. When these modes overlap, The resulting loads can be far greater than each acting alone. Mode coupling is a major reason why comprehensive BHA design, bit selection, and surface parameter control are all required to mitigate vibrations effectively. With this understanding, we now return to our original learning objectives to review how each has been achieved. Let's revisit the objectives we set out at the beginning of this submodule. First, we set out to understand axial, torsional, and transverse vibration mechanisms. We've examined each in detail from bit bounce to stick slip and whirl. Second, we aim to recognize stick slip effects and mitigation technologies. We covered both bit design and advanced downhole and surface tools such as AST and soft torque systems. Third, we evaluated BHA whirl and its impact on drill string integrity, noting its destructive effects even thousands of feet above the bit. Fourth, we identified mitigation tools such as shock subs and other vibration control technologies, weighing their advantages and limitations. Finally, we interpreted vibration modes and discussed how they influence drilling performance, especially when coupled. Let's now conclude the submodule. This concludes submodule 2 of 4 of drilling mechanics and shock and vibrations. Thank you for your attention and participation throughout this session. Please proceed to the short quiz to reinforce what you've learned. Your engagement in applying these principles will help ensure safer, more efficient drilling operations. Thank you once again.